Okay, thank you all for coming back. So this is my web page, and I am putting notes. You should only think that they're accurate up to as far as I got to. So the ones for the future, I'm still working on them. Nevertheless, they're posted there. So you go to my web page, you click on the link. I think it says notes, and then there should be a link that says Kyoto 2018, and the lecture notes should be there. So today I do want to start discussing how to actually run the minimum model program. We'll see how far we get. At least I want to discuss how to run the minimum model program. In order to tell you how to run the minimum model program, I first need to remind you what the Cone theorem says. So let's start by assuming that X is complex projective variety. I will assume that the dimension of X is, say, D. As I said, X is going to be complex projective, and I'm going to assume that it's normal and Q factorial. So if you have any divisor, well, the important thing is, say, with integer coefficients or with rational coefficient, then there exists some integer, m, some positive integer, let's just say m greater than 0, such that MD is Cartier. Right, so for smooth varieties, this is never a problem, but for singular varieties, it's an issue. So I'm going to assume that it's Q factorial. I've already defined the equivalence relation. So on the space, I consider the space of divisors with real coefficients. And on this space, I consider equivalence relation, which is the numerical equivalence relation. So D is numerically equivalent to D prime if and only if D minus D prime intersected with any curve C is always 0 for every C contained in X, a curve. Okay, so this is a finite dimensional vector space, and I denote by, so it's a real vector space, and I denote by rho of x the dimension of this vector space. Okay, so we'll give this vector space a name. We'll call it n upper 1 for codimension 1 of x. And this vector space is dual to the space of curves modulo numerical equivalence. So that would be n lower 1 of x dual. So this is curves up to numerical equivalence. So, you know, the n1 of x is generated by curves. And in a similar way, a curve C is numerically equivalent to a curve C prime if C minus C prime intersect with any divisor D is equal to 0 for every D here. Okay, so clearly they're dual vector spaces, and of course they're going to have the same dimension. Okay, so inside of n1 of x, I'm going to consider the cone and E of x. So this is the cone generated by linear combination of effective curve classes. So let me just write it as this way, sum of Ci, where Ci are honest curves, and Ci are non-negative real numbers. So this is clearly a cone. If you have two objects of this kind and you sum them together, you get another finite linear combination of curves with non-negative coefficients. Okay, so the cone theorem describes this, this cone in a very precise way and in a useful way for the minimum model program. So here's the statement of the cone theorem. So there's going to be 4 statements. The first statement is, well, I have to tell you what kind of objects I'm considering. This doesn't work for any Q factorial projective variety. So let's assume that XB is a Q factorial Kawamata log terminal pair. Remember, Kawamata log terminal pairs have mild singularities. Okay, so then the following four things are going to happen. So first of all, there exists a countable collection, Ci, of curves, which are rational curves, and such that when I look at the closure of the effective cone of curves, then this is spanned by two kinds of curves. Well, we can look at the curves kx plus b greater or equal to 0. So by that symbol here, I just mean so NEX kx plus b greater or equal to 0. This just means the curves C, which intersect with the cos kx plus b, are non-negative. Okay, so those are. This is the part of this cone which is in the positive half plane with respect to this, the hyperplane defined by this element of the dual vector space, plus the sum of greater or equal to 0 these classes Ci. So the cone is spanned by the non-negative part plus this countable collection of curves Ci. So of course these curves Ci dot kx plus b is less than 0. So I guess the picture, so usually the picture that you see is a picture of sort of three-dimensional cone. It's not so easy to draw a good picture. So this would be kx plus b dot c equals to 0. This would be the negative part, and this would be the positive part. So the theorem tells you very little about the positive part, but it says that the generators that you need on the negative part are spanned by finitely many rational curves. And the next statement that I say, sorry, countably many, and the only accumulation for these rays is actually around the hyperplane kx plus b equals to 0. That will be the next statement. However, one should note that this three-dimensional picture is always a bit misleading, because it leads you to believe that on this side of the hyperplane, the cone is locally rational polyhedral, which is not the case. So you should really think about, so this picture is somewhat misleading. I mean, it's accurate in this dimension. A better picture is something like an ice cream cone, and then a cone over that. Okay, so, and this would be your hyperplane. This is the kx plus b positive part of the hyperplane. So you're doing a cone over something that's not very nicely shaped. So you see, on this side, it might well not be locally polyhedral. So you have to be a little bit careful about not putting your expectations too high. You know, not overestimating what the theorem says, and this does sometimes actually lead to people making mistakes. So it's something to keep in mind. So now I'm going to make the statement that these rays only accumulate close to this hyperplane kx plus b equal to 0. So for every epsilon greater than 0 and h ample, I could have just said for any ample Q divisor, then NEX bar is NEX bar kx plus b plus epsilon h greater or equal to 0. So this cone, this is slightly bigger than this, right? If you have a curve, for example, that intersects kx plus b negatively, but a very small amount, then this epsilon h will win out, right? Because that's an ample class. It always intersects any curve positively. So this is increasing the size of increasing your hyperplane a little bit. It's eating up all the rays that are close to the boundary. So you only need a finite subset, and then you only need finitely many of these rays. Now, the next statement is something very useful about the negative faces. Suppose if f contained in NE x bar in this closed cone is kx plus b negative extremal face. I'll discuss in a second what this really means, negative extremal face. Then there exists a contraction morphism, let's call it CF from x to w. So contraction morphism is going to be a morphism of normal spaces with connected fiber. So the push forward of O of x will be O of w, with the property that CF lower star of C is equal to 0. So it actually contracts a given curve if and only if this curve belongs to the face. So I guess the numerical class of this curve belongs to that face. And finally, so I'll say a little bit more about this in 1 second, but let me make the last statement of the cone theorem. Suppose that L is Cartier and L dot C is equal to 0 if and only if C, the class of C, belongs to my face. So this is a Cartier, it's a line bundle which intersects trivially precisely the curves contracted by this contraction map C of F. Then L is equal to CF upper star of some line bundle was L.W, where L.W is Cartier on W. Okay, so notice that in general, you cannot always just give a numerical condition to say that the line bundle is pulled back via morphism, right? Because the typical example where this doesn't happen, so the typical counterexample is E is an elliptic curve, and C is the map to a point, and L is not O of x, but it has degree 0. Any topologically trivial line bundle, any deformation, for example, it could just be, so I guess x is E in this case. Any difference of 2 distinct points would be such a line bundle. Clearly, that's not the pullback of any line bundle on spec C, because any line bundle on spec C is trivial. But the degree with respect to any contracted curve of this is 0, right? Yes?
I think you will have only one F.
Only one F. This if and only if here?
No. The one lower. LC is equal to IFF, no?
Oh, LC is equal to 0 if and only if C is in F.
No, if
Yes. I got a bit carried away. Okay, so let me figure out which direction I wanted to say. If L is Cartier, and L dot C is equal to 0, if for any such curve, then it is the pullback. Of course, it could be that L is just a trivial line bundle. It's still the pullback, but it's 0 on plenty more curves. Yes, I did get a bit carried away there. Thank you very much for... No. We might as well be precise if we can figure out how to be precise. Actually, on the notes, I think it's correct, so I don't need to correct the notes. But yes. Okay, so negative extremal phase. So what do we really mean by negative extremal phase? So in the picture, it looks like this is a negative extremal ray, for example. Mostly we care about negative extremal ray. So how do you sort of quantify that? Well, the way that you quantify that, okay, my glasses are confusing me, so I actually managed to miss the point. It's really hard when you get farsighted and you need your glasses for your notes and you don't need your glasses for the blackboard. The older people in the audience can appreciate that. So you look for a line bundle L with the property that L is nef and L dot C is equal to 0 for every curve C whose class is in F, right? So in this case, the negative extremal ray face is just one-dimensional. It's a ray. And so this condition that L is nef guarantees that the cone lies on one side of L. It lies on the positive side of L. And the intersection of this hyperplane with the cone is your extremal face. That's an extremal face. And I say that it's negative because everything in that face intersects kx plus b negatively. Okay? So, and now if I have such a line bundle, I look at the contraction of the ray. I'm mostly just going to be interested in contractions of one-dimensional faces, so of rays. And then this line bundle is the pullback of a line bundle from downstairs. So that's the main picture to keep in mind. Okay, so I guess the natural question is, do we know of any examples of this? Well, we have already played around with some examples. So for example, X is perceptible surface Fn, then the N1 of X is generated by two kinds of curves. One, of course, is the fiber. So maybe I can sort of express that as a fiber by reminding ourselves that the self-intersection will be 0, right? Two fibers that don't intersect. And the other one, for example, you could take the horizontal section, this curve E, with the property that E squared is equal to minus n. Those two curves generate the cone. Well, in fact, they generate the if you only use positive coefficients or non-negative coefficients, they generate NE of X is generated by F and E. So in fact, these two should be extremal rays, if I haven't made a stupid mistake. So let's try and check that these two are extremal rays. Okay, so we could compute the canonical class and check that the intersection is negative. But maybe we can just write down the corresponding contraction. So there is one natural contraction from Fn to P1. Remember, Fn is just a P1 bundle over P1. So let's look at that contraction. And this contraction, this is the contraction of the fiber class. Right? That's what the fibers are. They're the fibers for that map. So that's an example, a very basic example of the cone theorem in action. And then if this is indeed the other face of your two-dimensional cone, okay, so this would be any multiple of the class of F, any multiple of the class of E. Okay, you want to write things down precisely, it takes a long time. So what does E do? Well, you can contract down E to get, maybe I'll call it Cn. This is a cone over a rational curve of degree n, right? So those are your two contractions in the setting, and you can check that they are kx negative. It's an easy computation. So that's one example. Another example is, suppose that we have X containing E, and this is a -1 curve. Well, then Castelnuovo's criterion tells us that we can contract E down to a surface, let's say, X bar, and E will go to a point P in X bar. And then, once again, E is a negative extremal ray with respect to this map. More generally, whenever you have a variety X with a smooth subvariety Z, and you blow up Z, you blow up X along Z, then you get a divisorial contraction, a divisor getting contracted to a subvariety of codimension greater or equal to 2. Okay, if Z has codimension 1, this operation does nothing. So let's assume that Z has codimension greater or equal to 2. And this is a P C, where C is the codimension of Z and X, PC minus 1 bundle over Z. And in fact, the negative extremal ray corresponds to a curve in a fiber of this map. So pick a line in one of the fibers of this map. On this map. So we already know several examples of that, and one can construct a lot of interesting examples. Maybe in the interest of time I won't do it, but you can, I think I worked out something in the notes. You can take cones over your favorite smooth variety, and depending on the numerics of your cone, you get a KLT variety of dimension 1 bigger, and when you blow up the vertex, you get one of these divisorial contraction, which is another example of contracting a negative extremal ray. As long as you work out the numbers right, which hopefully I did do in the notes if you're interested, and if you haven't seen it before. I should also say, maybe I won't work it out in full generality, but I should make at least one quick example to try and convince you that you could really have infinitely, countably many of these rays. It's not necessarily a finite sum. So there is a standard example. So what do? You consider, here's my picture of P2. You pick two general cubics. So you need them to be general. I think the reason why you want them to be general is you don't want, for example, think of these 9 points on one of the cubic. You don't want all of those points to be torsion. And you'll see in a second why. So pick two very general cubics, pick the points of intersection, blow up these points. So we're going to blow up P1 through P9. Then what we get is every point is replaced by, okay, I have to draw too many of these. We get 9 exceptional divisors, and now the cubics become this pencil of cubics. I'm just going to draw 2 of them, the 2 that I draw here, but really there's a pencil going through this point. This pencil of cubics becomes a base point free linear series, and so, right, because, for example, one way to see it is that E squared is 9 here. When I blow up 9 points, each time you blow up a point, it goes down by 1. E squared, the strict transform have self-intersection. So this is C1 and C2, C1 prime, C2 prime. The strict transforms have self-intersection 0, so they're fibers for a corresponding fibration onto P1, right? Because these exceptional divisors have to map surjectively onto the image, so that's going to be a P1. After all, it's a pencil of elliptic curves. It has to be a P1. Okay, so I'm going to try and give you a hint of why. So the claim is that N, E, X has infinitely many negative extremal rays. So, well, okay, so I'm in good shape because I already have 9 negative extremal rays, right? So, you know, the answer usually is 0, 1, or infinity. So if it's 9, it's probably infinity. So, but how can I start generating more rational curves with the same properties? Well, it would be useful if I had an automorphism of the surface over P1 that just, if you have any automorphism, it's going to generate other curves with the same properties, right? So the way that I'm checking that these are negative extremal rays is by checking that they're -1 curves. EI squared is equal to kx dot EI, which is equal to -1, right? So, okay, so you think about it for a second and you think, well, okay, so we have elliptic curves here. And elliptic curves have interesting automorphism groups. So maybe we can use the automorphisms of the elliptic curves to do this. So the way you want to think about it, if I remember correctly, is you take the generic fiber, which is an elliptic curve over the field corresponding to the generic point of P1, so over K of T. And you want to check that this fiber, that you can do translation by a non-torsion point. Because if you have a non-torsion point by which you can do translation, then what that's going to do is going to translate these sections to other sections, and since it's non-torsion, you will be getting infinitely many other sections. So how do you make sure that you have a non-torsion point? Well, you know that you have these 9 points corresponding to the generic point of each section, and now I've picked these very general so that I can assume that the ratio of the difference between two sections is not a torsion point. So that's the point of, why I need to assume that these are chosen generally. Okay, so it's not a complete proof, but hopefully it gives you a hint that there should be many negative extreme array, many -1 curves in this case. Other examples of interesting cones, not necessarily negative cones, for example, when you consider most K-free surfaces have interesting cones, and most abelian surfaces. So for example, pick a product of 2 elliptic curves, then it tends to have a round cone. Of course, the canonical class of a K-free or of a abelian surface is trivial, so you're not going to get a whole bunch of Kx negative extreme arrays. You'll get a whole bunch of Kx trivial arrays. In fact, you'll get a round cone. So and luckily, I can't hesitate too much, otherwise I won't get very far. Okay, so for now, we're going to take this as a black box, but I'm hoping today to do part of the proof of this, to tell you what the sort of main ingredient in the proof is. But let's see how we use it in terms of running the minimal model program. So what I'm going to do now is the traditional way of running the minimal model program, and then I'll explain why eventually we need to do it in a slightly different way. So the traditional way allows you lots of freedom, which for many applications is good, but eventually I'll tell you why it's also bad. So let's do running the minimal model program. Okay, so remember, the goal is to end either with a minimal model or a Mori fiber space. Okay, so what do you start with? So the input, it's important to start with the right class of object. So the input will be a pair xb, which is KLT and Q factorial. And of course, you want it to be complex projective, but I'm not, that's assumed throughout the lectures. If you're still not in love with KLT pairs, you could even think to start with X terminal, or even smooth if you prefer, but it won't stay smooth throughout the process, B equal to 0, and of course, X Q factorial. And there are other flavors. So if you know what a DLT singularity is, you could run this in the DLT world, and so on. But let's just focus on KLT pairs, or if you prefer, smooth terminal varieties with empty boundary. Okay, so what's the first thing you do is you ask yourself, have I already won? So if K of X plus B is nef, then X is a minimal model. Let me just write MM, and we have 1. Okay, so that was easy. Let's see how the rest goes. Otherwise, if K of X plus B is not nef, then by the cone theorem, I can pick a negative extreme array. So I'll do that. Pick a negative extreme array, And I'm going to consider the contraction of this negative extreme array. So that's just a one-dimensional face, this negative extreme array. I'm going to consider the contraction morphism. I want to use the same notation that I have here. So it's going to go from X to W. So this is a contraction defined by the Cohn theorem. Okay, so very well. So what could happen? Well, we could have the following situation. One is easy, I'll put it here. If the dimension of W is less than the dimension of X, then the map from X to W is a Mori fiber space, right? Because the conditions for Mori fiber space were that this dimension is smaller than that dimension, and the most important thing is you need that minus kx plus b is, this map is C, is relatively ample, is C ample. But you see, since I have picked an extreme array of one-dimensional subspace, it is easy to see that the relative Picard, relative Picard group of X over W is one-dimensional, right? Everything that intersects contracted curve 0 is pulled back from downstairs. So the only interesting number is the intersection with a generator of the extreme array. So it's very easy to check that the relative Picard number is 1. Of course, we know it's a negative extreme array, so the intersection with kx plus b is negative. So the intersection with minus kx plus b is positive. Relative Picard number is 1. It has to be relatively ample. Okay? So this is a Mori fiber space. And we declare victory. Okay? So what's the remaining case? Well, suppose that the dimension of X is equal to the dimension of W. So now it's a birational map. And suppose that the dimension of the exceptional set of this contraction C of R is the dimension of X minus 1. This is a good case, because this reminds you of the contraction of a minus 1 curve on a surface, right? You're contracting a codimension one subvariety. So then, okay, for now it's a claim. W is Q factorial, and KW plus BW is KLT, where BW is just the push forward, the strict transform of B. Okay, so maybe I'll underline it in pink to remind ourselves that we should try and convince ourselves that this is true. Right? But if you believe that we're still in the same category, then you should be pretty happy. Then you replace XB by WBW and repeat. This is just what you did for surfaces, right? You contracted the minus 1 curve, and then you look again. Are there any other minus 1 curves? If so, contract it again. At a certain point, you run out of minus 1 curve, you have your minimal model or your Mori fiber space. Okay? So the problem here is, what do we do if the dimension of X is equal to the dimension of W, the one remaining case, and the dimension of the exceptional set of CR is less than the dimension of X minus 1. Or let's say less or equal to the dimension of X minus 2. Okay, so this can only happen, it cannot happen for surfaces, it can only happen in dimension 3 or greater, and it really happens in dimension 3 or greater. It's easy to construct examples. What do we do in this case? Okay, so I'll write down some claims, and we're going to check the claims in a minute. So I'll underline them in pink, the stuff that is not justified in any way. Okay, so but I claim that then W is not Q factorial. Even worse, KW plus BW is not Q Cartier or R Cartier. Let's say that we're working with two divisors, Q Cartier, and this makes me very unhappy, right? Because I went out of my category. If this gadget is not Q Cartier, it doesn't even make sense to ask the question, is the singularity Kawamata terminal? It cannot be a Kawamata terminal singularity. Right? So this is a kind of singularity that I don't know how to deal with. I look at it and, even I start looking at I try to look at the cone theorem for this. That doesn't make sense anymore. There's all kinds of technical issues. So that's not a good replacement. So what do we do? So, well, we follow what Mori did in 3 dimensions. So we do something known as a flip. So we look at the following ring. So let me, it's going to be a local question. I'm wondering if I should write it. Okay, maybe I'll just write it. So consider the following algebra of OW modules. So it's a direct sum of the push forward of OX, this map is C, push forward of OX M KX plus B. So this is the direct sum over M greater or equal to 0. So we look at this guy, and so if it is finitely generated, so maybe I should give this guy a name. So I don't know, let's call it fancy A. So if this is fancy generated as an OZ algebra, then let X plus be defined by proj of this algebra as an OZ module. Okay, so I'll try to make this a bit more digestible now, and then I'll go and actually prove a few things. So maybe the way you want to think about it is the following. So, I mean, I'm going to just rewrite it in slightly different terms, but I found that a lot easier to digest the first time I saw it. So, we're trying to show that we want A finitely generated as an OZ algebra is a local question over Z. So assume Z is affine. Just makes your life a little bit easier to think that Z is affine. Then what are we really asking for? Then we can identify C lower star of OX M KX plus B. We can just identify that as global sections of M KX plus B. And then what we're really asking is we want the ring corresponding to KX plus B. So this is the direct sum for all M greater or equal to 0 of H0 M KX plus B to be finitely generated, right? So this is a local version of one of the original problems, the finite generation of the canonical ring. Yes?
What is Z? W.
Oh, yes. Z equals W. Okay, so let's make some corrections. I think I used W more than Z, so let's fix that immediately. I'm not sure I used more Z's than W's. There seem to be a lot of... Okay, yes. Okay. OW. Okay, other questions? Or mistakes? Okay, so Okay, now what you need to see is the following claim. The claim is that this map from x, so we have a map from x to x plus, maybe I'll call that phi. This is happening over z. So phi is a small birational isomorphism. So small means that these are isomorphic in codimension 1. Everything in the picture is isomorphic in codimension 1. Right? Remember, I know that this map does not contract any divisors. So this is clearly isomorphic in codimension 1. So what I'm saying is that I haven't extracted any divisors. I haven't created any new divisors on x plus. It would be nice if x plus is q factorial. It would be nice if x plus b plus is KOT, where b plus is just a strict transform of b. And finally, it would be nice if I've improved the situation, right? Because I don't want x plus to be equal to x. That doesn't take me anywhere. So I want kx plus plus b plus is ample over z. So that's the last property is the reason why it's called a flip, because you're replacing some kx plus b negative curve by a kx plus b positive curve. So here you have a curve, let's call it c, kx plus b dot c is less than 0. Maybe this map is just contracting that unique curve. And maybe on this other side, you have another curve, which is they're probably both rational curves, but they're embedded in x in different ways with different normal bundles. So for this curve, kx plus plus b plus dot c plus is positive.
I have a question.
Yeah, did I make a...
So assume W is affine, then C lower stuff, the left-hand side is a sheaf, and the right-hand side.
Right, but on an affine variety, a sheaf can be identified with its global space of global sections.
Oh, that's what you mean.
That's exactly what I mean, yes.
Oh, okay.
Right, so it's just a psychological thing.
Okay.
So first of all, it's not equal. This is, there's a functor that goes from, you know exactly what we're talking about. Yeah, so this is, there's an equivalence between these two objects. And the functor is take global sections. Yeah. And going the other way is you do the tilde thing. And there's no difference between the two. It just sometimes it's psychologically easier to think in these terms. And once you think on these terms being finitely generated over Z or finitely generated over C, it's the same thing because Z is finitely generated over. Right, so there's several reasons why psychologically it helps, but in the end it's the same exact thing. Other questions, other things that are not clear before I try to prove some of these outrageous claims that I made.
So Z is W.
Oh, for crying out loud, yes. So I don't know why in these lectures No, it's perfectly legit. Okay, other questions apart from Z being equal to W? No questions that come to mind? Okay, so there's a whole bunch of claims that I made. Maybe I won't prove all of them, but I should at least give you some feeling of how these things work out. So the first thing maybe that it would be nice to see is, well, I made a claim that when you have a flipping contraction, the target is not KOT. So why do I need to go to all this trouble? So let's start with that. So we're looking at x goes to z, a flipping contraction, w, a flipping contraction, and I want to show that kw plus bw is not, we're working with Q varieties, let's say, so it's not Q Cartier. But the same argument works if you work with R divisors, it's not R Cartier. So let's prove this. It's almost a triviality. If not, then I can consider the pullback of KW plus BW. Now I claim that this is just KX plus B. How can I be so sure? Well, these things are isomorphic in codimension 1, right? So those two divisors agree outside of a codimension 2 set. If two divisors agree outside of a codimension 2 set, they are the same thing. So we have this equality. But now let's intersect with, so let's let C be a generator of the rate that I contracted, greater or equal to 0 to be precise. So let's intersect with C. So I'm going to intersect with C. So on this side, I get 0 when I intersect with C, because this is a pullback of a Q-Cartier divisor. And so it's a linear combination of honest Cartier divisors with real coefficient. Each one of them is pulled back from downstairs, so restricts to a trivial line bound on C. So its degree is 0. So this intersection number is 0, just by the projection formula. On the other hand, by assumption, this number here, Kx plus B dot C, is negative, right? It generates a negative extremal rate. That cannot be. Contradiction. Okay, so of the many, many things that I have claimed, we believe this one now. Okay, so maybe I should now try and convince you that if we have a divisorial contraction, so X to W, a divisorial contraction, then W is Q factorial, and KW plus BW is KLT. Okay, so how did this go? Well, let's use the information that we have. We know that we have a divisor in here, which is exceptional. And so we know one can easily check, but it's not really important for the argument, so I won't bother right now, but that's an interesting exercise. One can check that, in fact, E is irreducible. The point is that the relative Picard number is 1, so if you had more than one component of E, you can easily intersect it with some curves and get sort of different answers. You can show that the relative Picard number is bigger than 1. So let's just assume that. Okay, but E is not numerically equivalent to 0. In fact, okay, yeah, that's, well, in fact, we can check that E dot C has to be less than 0. Right? Because that's, what's that? That's a negativity lemma, right? Because if it were numerically equivalent to 0 and exceptional, then it would actually have to be 0. And I just picked an effective exceptional divisor. And then other part of, if you think about the negativity lemma, any effective exceptional divisor has to be, cannot be NEF, so it has to be anti-NEF. And since the relative Picard number is 1, it's actually anti-ample. Right, so just keep in mind that the relative Picard number is 1, which makes all of your computations extremely easy. Right? The only thing you care is one number, if it's positive or negative with respect to the curve that you're contracting. Okay, so now I can pick Kx plus B plus, so this intersects the curve negatively. Let's say minus AE. I can pick A such that this intersects C is equal to 0. Why is that? Well, you just solve this equation, right? So in other words, you set, or hopefully I do it right, A should be equal to Kx plus B dot C divided by E dot C. And that's why I took care to check that E dot C was non-zero. And in fact, it's negative, and this number is negative, so this A is greater or equal to 0. It's strictly greater than 0 in fact. Okay? Okay, so now you see we have a Q-Cartier divisor. This is a rational number. These intersection numbers are rational. So this is a Q-Cartier divisor with the property that it intersects every contracted curve 0. So then M, some multiple, as long as M is sufficiently divisible, this is going to be Cartier, because X is Q factorial. And this is Cartier, it intersects every contracted curve trivially. So in fact, M kx plus b minus ae has to be the pullback of some divisors from downstairs. What divisor? Of course, it will be the pullback of its push forward. There's no other choice. So it has to be the pullback of M kw plus bw. So I have shown to you that kw plus bw is Q Cartier. And in fact, I've done much better. So in fact, I've shown that, let me write it this way, kx plus b is equal to the pullback of kw plus bw plus ae. So the discrepancies for WBW are actually greater or equal to the discrepancies for B. So let me write that formally. So if you pick F, any divisor, over X, and you compute the discrepancy, AF, with respect to XB, that will be equal to the discrepancy with respect to WBW, minus A times the multiplicity along F of E. Okay, so the only mystery is this a plus or a minus, right? Because it's, remember, the discrepancy are the negative of the multiplicities of the divisors, right? So if I look from this equation, when I pull back this equation, the multiplicities that I get from this guy, I have to increase them by A times the multiplicity of E along that divisor to get the multiplicity of B. So the multiplicities of B are bigger, so the discrepancy should be smaller, which is what I wrote. It's very annoying getting the sign right. After you play with it for 20 years, you sometimes get it right. Okay, so what this is telling us is, now we know by assumption that these guys are greater than -1 because this is KOT. But then these guys are even possibly bigger, right? Because this is a positive, non-negative quantity. So this is telling us that AFWBW is greater or equal to AFXB, which is greater than -1. So it tells us that WBW is in fact KOT. But it tells us slightly more. It says that discrepancies improve. So we have the strict inequality if and only if the center of your divisor is contained in E, right? If the center of F is contained in E, that's precisely when the multiplicity of E along F is strictly positive. So in some sense, in this purely numerical sense, the discrepancies, the singularities are actually improving. Okay, well, this is not the naive sense. So you could very well have a situation in which you have a smooth variety and you have some subvariety that you contract down to a point. So you create a singular variety where all the discrepancies on the singular variety are greater or equal to the ones on the smooth variety. So in some sense, this is less singular. But actually, this one is smooth and this is non-singular. So from a sort of a cohomological sense, this one is better behaved than the smooth variety. Right? So let's just say that the discrepancies are a sophisticated way of gauging the singularities, which doesn't always match with our intuition. OK, so any questions on these two computations that I made? No questions. OK, so what I think I should do, maybe I'll say a couple more words about these properties. Maybe we don't want to spend too much time checking everything in detail. That does give you a sense. Maybe I should examine the flips a little bit and try to get a little bit better intuition on why those four properties hold for flips. They're all trivial properties, but it's easy to get confused about it. So the first property that I claimed somewhere is that phi is small birational. So why is this a small birational morphism? So let's think about how we construct that. So, OK, so we're assuming, we haven't proven it, but we're assuming that this is finitely generated, right? So what you're really doing, so let's assume, say that this ring R of kx plus b is generated in degree m. So even saying that is a bit odd. What do I mean by generated in degree m? What I mean is that if I consider the ring direct sum of H0 m k kx plus b, where k is greater or equal to 0, so I'm looking at the corresponding Veronese subring, I mean that one is generated in degree 1. Okay, well then, in that case, how can I view this map? Well, let me take a resolution, let's call it P, x prime. So P is a resolution of this linear series. So what I want is that pullback of m kx plus b is given by a mobile part plus a fixed part. Well, that's always true. And I want the fixed part to be a divisor. Well, if you take a log resolution, this will be a simple normal crossing divisor. But what I really care about, I'm not really so worried about that. What I really care is that m be base point free, right? Because how are you really going to define the rational map corresponding to a linear series? Well, you go to a resolution where that linear series becomes base point free, and then you actually have an honest morphism. So you get a map here, let's call it Q to x plus, and under this map, Q upper star of the hyperplane class on x plus, which I denote just by 1, OX1, will actually be M. OK? OK, so now the question is, by construction, all of this is happening over W. Now the question is, why is this map small over W? So I extracted a whole bunch of divisors here, right? And I'm claiming that I have to contract them again to get down here. OK, so let's think about the following. Let's think about the linear series corresponding to M plus F plus E, where E is any P exceptional divisor. So if you think about it for a second, if I add a P exceptional divisor to something that's pulled back from X, I'm not creating any new sections. The sections are exactly the same. So that, what I just said, means that this linear series will be the same as M plus F plus E. OK? So now, M is the pullback of an ample divisor on X plus. So I need to argue, and hopefully I'll get it right, that when that this equation, it doesn't just hold for M. This equation here actually holds for any multiple of M, k m plus f plus e equals km plus kf plus ke. So this fact now forces e to be exceptional. Right? So the quick way sort of to visualize it is to think of sort of, you know, you're expecting the rate of growth of this linear series to be more or less like the top self-intersection of this divisor.
Is Q exceptional? Q exceptional.
It doesn't matter because
No,
P...
what the conclusion
it's,
is Q exceptional.
yes, yes. So what I want to show is that it's Q exceptional. That's what I need to show. Yeah. So where was I? Okay, so I'm trying to convince myself that it's Q exceptional. So let's see. So let's think about the following. We have a map from O x prime to O x prime, add your favorite exceptional divisor. And now you twist this by Km and you push it forward. So then you have a map from, when you push it forward, you get a map from Ox plus K to the push forward of Ox prime E twisted by Ox plus K. So this becomes a sufficiently ample divisor and the sections are the same. So what's that telling you is that Q lower star of Ox prime E is actually going to be isomorphic to Ox plus. Now that will happen if E is exceptional, but not if E is not an exceptional divisor. Right? So this is just a sketch. Maybe you have to think about it a teeny bit to really convince yourself that I haven't cheated. But you can get the details right pretty quickly. This tells you that E is exceptional. So any P exceptional divisor is actually Q exceptional, so this map is also smooth. Then I've written it down in the notes, but checking that x plus is Q factorial and kx plus B plus is Q Cartier is relatively straightforward, and checking that the singularities have improved, it's exactly the same computation we did over there. It's just applying the negativity lemma. So, yes?
Q exception. Sorry.
Yeah, it's a habit that it's hard to, just like calling something Z, it's hard to get rid of it because at the end of the day, a divisor, you know, once I've proven that it's Q exceptional, then these two isomorphic in codimension 1, so saying exceptional for this guy and exceptional for that guy is the same thing, and so yes, it's hard to grow out of it. Okay, so I think I'll stop here for now so we can take a break, and then we'll continue. Thanks. I see one person coming. Let's wait a second. That person, yes. I think he might be right. Okay, so the two main issues remaining is issues prove that flips exist. So whenever you have a flipping contraction, then the corresponding algebra is finitely generated, so you can take product of that algebra and you can flip. And then the next issue is prove there are no infinite sequence of flips. This is known as the termination problem. And this is known to be true in dimension of x is less or equal to 3. So why is it enough to show that, that we have termination of flips? So I sort of alluded to it, but maybe I didn't write it down. So if x to w is a divisorial contraction, then we have that the Picard number of x is equal to the Picard number of w plus 1 if x, let me just write to x plus now, is a flip, then the Picard number is unchanged, right? Because this is happening over z, and one can show that both relative Picard numbers are 1. So that number is unchanged. So whenever you have a flip, the number is unchanged. Whenever you have a divisorial contraction, it goes down by 1. It's a positive integer. This can't happen infinitely many times. End of story. The only issue is, can I have an infinite sequence of flips? So, so the question is, why should you even believe for a second that you can't have infinite sequences of flips, right? So the point is that now flips improve x. In what sense do they improve x? Well, I've tried to claim that they improve the singularities of x. They AE xb is always less or equal to AE x plus b plus, and in fact it strictly increases for and it's actually not equal, it strictly increases for any any exceptional divisor E with center which is contained in the exceptional locus of the map from, I called it C, from X to W. Okay? I don't know why I put Z again here. Okay, so if you have some divisor that maps to a curve that's contracted by the flipping contraction, then the discrepancy has to strictly increase. So for example, if you knew that all of these were numbers and they can't get too big, you would quickly get a contradiction, right? Remember, there's one of Shawker's conjectures says that the minimal log discrepancy is bounded from above. So I should mention that Shawker actually has a beautiful argument that makes this precise. So there's a theorem of Shawker that says that if you believe, so let's assume if you're a believer, his ACC conjecture for minimal log discrepancies, you can ignore the log, just think minimal discrepancies, plus his semi-continuity conjecture, for minimal log discrepancies. So if you assume these two very natural but very bold conjectures, then flips terminate. Okay? So if minimal log discrepancies really are the measure of singularity that we hope them to grow up to be, then they will do the job that they're supposed to do, prove that any sequence of flips has to terminate. You cannot have an infinite sequence of flips. So the semi-continuity, roughly speaking, is telling you that you can stratify X according to how singular each strata is in terms of the MLD value of that point, right? It's a semi-continuous function, so it stratifies X into a finite union of locally closed subset. From this property, we know that these values along the stratification always improve, and some of them strictly increases. And the conjecture on the ACC for MLD tells you that you cannot have an infinite strictly increasing sequence. So if you put those together in the right way, then you actually get the theorem. Right.
How come you said you can omit L, meaning M?
Oh, because I haven't told you what the MLD is. So let's call A star of E x b the MLD. Then that is just the usual log discrepancy plus 1. And so this is convenient because, for example, if you take the log discrepancy over, say, a closed point, say the origin of Cn with respect to the divisor 0, then this will be A0 Cn empty divisor, we've already seen that if we blow up a point in Cn, plus 1, the discrepancy we get is n minus 1 plus 1 is n plus 1 is equal to n. And so it's more pleasing to see that for Cn, the minimum log discrepancy of a point is actually equal to n. And for certain statements, it's easier to write in terms of log discrepancy instead of discrepancy. But that's all there is. That's all. So saying that a set is well ordered or that set minus 1 is well ordered, they're equivalent statements. That's why it's OK. So maybe that's all I'll say about termination of flips for right now. Termination of flips in full generality is completely open. But what do we know how to prove? OK, so these are the results that we do know. So theorem.
So KLT termination in dimension 4 is open?
OK, so the state of the art is that termination of flips with scaling, which I'll describe in the next lecture, in dimension 4 holds in full generality. Termination of arbitrary sequence of flips holds by a result 2 months ago for pseudo-effective pairs. It always holds by a result of Moraga. And for non-pseudo-effective pairs, it's still open even in dimension 4 for KLT pairs. So that's the quick summary. So here's the theorem. Let f from x to z be a projective morphism of quasi-projective varieties where xb is a KLT pair, then the ring of kx plus b over z, now I call it z finally, is always finitely generated, where what does this ring here mean? This is the direct sum of the push forwards of ox m kx plus b, where m is greater or equal to 0. And in order for this to make sense, I have to assume that this guy is actually a Q divisor. I usually think of my KLT pairs as being Q divisors, but sometimes I have to allow them to have R coefficients. If I allow it to have R coefficients, I can't say that it's finitely generated. It won't be. I have to find a different way of stating that. It's, morally speaking, it's finitely generated. It's just like, in some sense, a semi-ample divisor. So this is always true. You don't need any hypothesis except that you have a projective morphism and a KLT pair. So for example, take any smooth complex projective variety. Its canonical ring is finitely generated in full generality. So the next one is the following corollary. So suppose that xb is KLT. F from x to w is a flipping contraction. Then the flip, let's call it f plus, from x plus to w exists. Right, so flips exist in full generality because if I state the finite generation theorem in this way, it includes the case of flips. And another corollary, it's not a trivial corollary. So if we have f from x to z, some projective morphism, and xb KLT pair, such that kx plus b is big, or b is big, or kx plus b is not pseudo-effective, then there is a minimal model program that terminates. So I'm not claiming that every minimal model program terminates. I'm claiming that there is at least one minimal model program that terminates. And in fact, I'll tell you in a second how to get that one, okay? It's known as the minimal model program with scaling. And so maybe I should also mention the last one. So in this case, so kx plus b pseudo-effective means that I have x equals x0 to x1 to x2. I mean, I've already said this, but it bears repeating, to xn. This is a minimal model. So kxn plus bn is nth. And in the not pseudo-effective case, we get x all the way up to xn, and then we get a map of modified space. So minus kxn plus bn is ample over z. Okay, let me mention one more corollary, then I'll tell you about the minimal model program with scaling. Okay, so what's the other corollary? Yes, please.
So you started with f going from x to z, but your condition is x plus b is big.
Okay, so yes, so the way I stated it, let's just say if x is projective. But you can write, you also have the relative version, but it seems a bit overkill. So if it's projective over z, you can do this over z, so this will be a map to some z prime over z, blah, blah, blah. So the relative version also works, but I sort of decided that it was overkill to write the way. The other thing is corollary, if kx plus b is big, then we can take x to be x canonical, the canonical model, proj of kx plus b, the log canonical model. So what properties does this have? So first of all, what happens is you do your finite sequence of flips and divisorial contractions to your minimal model. So on your minimal model, kxn plus bn becomes nth and big. And then by the base point free theorem, which I'll discuss soon, that's essentially one of the main ingredients in proving the cone theorem. The base point free theorem tells you that, in fact, when you have a KOT pair, which is neth and big, then kxn plus bn is semi-ample. So some multiple of that actually defines a morphism, and it defines a morphism to the canonical model. So this is just like in the theory of surface, where first you contract all down your -1 curves, and then you contract down your 0 curves. Right? And so you may be wondering why, for example, I introduced terminal and canonical singularities at the beginning. So if b is equal to 0 and x is terminal, for example, smooth, then this would give you that the minimal model has terminal singularities, and the canonical model has canonical singularities. Right? When you're going from the minimal model to canonical model, you may contract some exceptional divisor, which intersects the canonical class trivially. So when you do this game of comparing, comparing one canonical class with the other, the difference is 0, and so it's, that you're extracting something of discrepancy 0, so it cannot be terminal, it's just canonical. And So, you know, these canonical models, they have this beautiful feature that kx canonical plus b canonical is ample. And so those are the objects that you want to use for trying to define a nice modular space. Right? So with a lot of work, we now have a nice working theory of modular space of canonically polarized or log canonically polarized pairs, which I'm not going to go into now. Okay, did I want to say anything more about canonical models? What I would like to say, maybe I should say a couple more words here, is that X canonical is uniquely determined. I gave you a formula. It's proj of something, right? There it is. This ring is birational invariant. It's proj of that. It's uniquely determined. The minimal model, this depends on choices. It's not unique. But there are finitely many in the big case. So canonical models really are much better for many purposes. And maybe I should say, I'm debating on what the next step should be. Maybe I should tell you now about the minimal model program with scaling. Okay, so somehow I'm claiming here that as a corollary that if you take, you can choose a minimal model program which ends with an honest minimal model. You don't go around in loops. I'm only claiming that in the case that either B is big or kx plus B is big. Okay, so what is this minimal model program with scaling? So you want to think about it in the following way. You assume, so instead of just starting with your favorite KLT pair kx plus b and looking for the minimal model, you add an auxiliary divisor h, which will be a scaling divisor, with the property that this is nef. Okay, so first time you see this, it might bother you a bit. You're like, which divisor do I add? Doesn't matter. There always is such a divisor. Just assume that h is sufficiently ample. E.g., h sufficiently ample. Right? You take an ample divisor, you add a ridiculously high multiple. Eventually, that will become ample. And so now we scale it down. So we let T1, let's say, be the minimum. Well, technically I should say the inf, but it's actually a minimum. The set of T greater or equal to 0 such that kx plus b plus th is nef. And this is less than 1. Less or equal to 1. Right? Okay, so now you'd like this to be a rational number, for example. You have lots of questions about this. But if b is big, so when b is big, the case you want to think about is a case where b is of the form b plus a very small multiple of an ample divisor. In that case, we only have finitely many negative extreme arrays to worry about. In that case, we can guarantee that, in fact, t is a rational number, and this threshold is reached because you're cutting a negative extreme array. You encountered a negative extreme array. If b is big, then there exists a negative extremal, let's call it negative extremal ray R, which is spanned by a curve, let's call it C, such that kx plus b plus t1h dot c is equal to 0.
Chris,
Yes?
would you repeat the argument where you use the b is big?
Let me try and indicate it with a picture.
Yeah.
So this is the picture that you have in mind. When b is big, you are expecting that the number of negative extremal rays is finite, right? So b big means that I can think of b as some b prime plus epsilon ample. So then there are finitely many negative extremal rays to worry about, right? So and so now we started with this hyperplane kx plus b plus h, which is nef, so everything is on the positive side of this. And now we shrink this factor here. Okay, there is one case. There's one case that I didn't consider. If t1 is equal to 0, then kx plus b is nef, and we're done. Okay, but barring trivial cases, so now assume that this is kx plus b intersect c equals to 0. You are, as I shrink the factor t, this hyperplane is moving towards this hyperplane. Eventually, it will intersect the cone, and when it does, it could cut out a bigger dimensional face. It will cut down some face, right? And you just pick a subface, a one-dimensional subface of that. So you pick a ray contained in that face. And we need this bigness to ensure that there's no sort of accumulation of these rays that are creating a problem.
Thank you.
No problem. Okay, so we've selected a very special ray. So now we let x to w be the contraction of that ray. And we flip or we contract. So let's assume it's a flipping contraction, because those are the more scary, but it doesn't really make a difference. So let's assume it was a flipping contraction. So we want to replace x by x plus. Okay? But now, notice, kx plus b plus th dot c is 0. So in fact, kx plus b plus t1h is equal to the pullback via this map of kw plus bw plus t1hw by the cone theorem. And so kx plus plus b plus plus t1h plus, the strict transform, will be, I don't know, I want to call this map maybe C plus, will be the pullback via C plus of the same thing, kw plus bw plus t1hw. Okay, so now, by assumption, this guy is nef. Nef being nef is a closed condition. So this guy is nef, right? Because if something is the pullback of something else, it's nef if and only if it's a pullback of nef. It's an easy check. But now, this guy is nef, so this guy is nef. So not only can I do my flip and replace x by x plus, but the condition, well, kx plus b plus h will no longer be an f, but kx plus b plus t1h will now be nef. So now in the second step is we let t2 be the infimum of the set of t greater or equal to 0 with the property that kx, okay, so let's call this one x2 maybe, kx2 plus b2 plus th2 is nef. This is clearly less or equal to T1. And if it's 0, we won. If it's not 0, we pick the negative extreme array and repeat. So proceeding in this manner, we get a sequence of steps of the minimum model program. X equals x1 to x2 to x3 to x4. And numbers t1 greater or equal to t2 greater or equal to t3 with the property that kxi plus bi plus ti hi is nef. Okay, so why should we, on earth, should we expect that this minimum model now has to terminate? Right? So the claim, which maybe I won't prove today, but I will get to at some point, and I'll give you a sort of moral reason why it should be true. The claim is that there are only finitely many minimum models for pairs of the form x, b plus th, where t is in the interval between 0 and 1. Now, proving something like this relies very heavily on assuming that b is big. So assume that b is big, then I ask you to believe that there should be only finitely many models, minimum models for x, b plus th, where t is in that interval. So why does that do it? You know, there are a few technical issues to worry about, but the intuition now is very clear. If there can only be finitely many possible models in that, then the only thing you have to check is that every time that you do a flip, or a bunch of flips, you cannot have two of these actually be isomorphic. So, but we claim that in our sequence, xi to xj is never.
Could you ask a question?
Just a second. Never. Let me just write down. Never an isomorphism for every j greater than 9. Yes, please.
In the claim, you fix some t. You first fix some t.
No, I don't. I look at the set of all minimal models for pairs of the form x, b plus th, where t varies in 0, 1. And I claim that there's only finitely many. And I'll give you a very good intuitive reason. Then we'll do a formal proof later on. But I'll give you a very good intuitive reason in a second. Okay? So believe this. Then if you had an infinite sequence, eventually you have to get back to the same guy. Most likely, 1 and the next one, right? But you see, why is it never an isomorphism? Because just pick AE, XI, BI would have to be strictly less than AE for XJ, BJ for any E with center in the exception locus for the map from xi to zi. The map where in the flipping locus. Right? Remember we proved, or maybe I'll prove it again since I only proved it for divisor contractions. But we claimed, and we proved it for divisor contractions, that for each step of the minimum model program, the discrepancies never decrease. They're always non-decreasing, and they strictly increase if the center of your exceptional divisor is contained in the indeterminacy locus. So I just focus on one whose center is contained in the indeterminacy locus. It's strictly different, but if this is an isomorphism, then it should be the same. That's your contradiction.
I'm slightly confused.
Sure.
Because suppose I have P2,
Mm-hmm.
and I add the boundary, ample boundary, and so that it will become a pair. But then I can add some ample, and these will have, all of them are minimum models because it's ample.
All of what? A minimum model.
So suppose I'm P2, and B is three lines, and when you are adding little bit of ample, and all of them are, the ambient space is the same, but as a minimum model, they're different. So I don't know.
Okay, so I need to make the statement slightly more precise so I will do that. So, but note that the support of this divisor is fixed.
Including the boundary.
Wait.
Is this BI or BI plus?
No, it's just BI.
Just BI.
Yeah, I've done things right, but I agree with you that being more precise with the statement would be a good thing, right? So I've sort of, this is more or less the philosophy. Then I'll write down a very precise statement, but sometimes just writing the very precise statement, it's very dry. And okay, so here I'm really just claiming the only thing I want to conclude is that the map between the xi is an isomorphism. It's an isomorphism on an open set, but it's actually an isomorphism everywhere, which sends these divisors one to the other. Well, it has to because, but
now I understand.
yeah. And then if you want to think about the h, the support of the h is getting mapped into it. The coefficient is, of course, changing. Okay, but I'll write down a more precise statement, and then the statement should become more transparent. Okay, so, well, let me give you a little bit of intuition why something like this should be true. So I'm not writing down this precise statement still, but anyhow. So let's consider the following kind of Cox ring like object. So I'm going to consider the ring corresponding to kx plus b and to kx plus b plus h. So by this, I mean the direct sum for all m and n integers, non-negative integers, of h0 of m kx plus b plus n kx plus b plus h. Now, if you believe that the previous ring I discussed is finitely generated, you should also believe that this is finitely generated. You can construct some n+1 dimensional variety whose log canonical ring corresponds to this object.
So is this still KLT?
Sorry?
Is this still KLT? I mean, x, b plus h.
So kx plus b plus h. You should probably, yes, you should probably assume that it's KLT to begin with. The argument, there may be a proof even if it's not KLT, but let's assume it's KLT. Yeah. I'm being a bit vague here. For this argument that I'm giving you now, you have to assume that that's KLT. Okay, so let's assume. Right, yes. Yeah. But I said, just start with this guy being Neff. You could still do that, and then
No.
Split up the coefficients. I think the best thing to say is assume is Neff and KLT. This property will also be preserved. This property will not be preserved. What will be preserved is that this guy is Neff and KLT with this smaller value of t, with this value of t less than 1. That's so each step of each one of these flips will actually be negative with respect to kx plus b plus th where for any t less or equal to ti. So it will preserve the singularities of that object, but not necessarily of kx plus b plus h itself. So you're worrying about technicalities that at some point you have to worry about, but I'm trying to sweep under the rug. So if you believe that this thing here is finitely generated, so you sort of visualize it as corresponding to two axes. One corresponds to kx plus b, and one corresponds to kx plus b plus h. And the generators are, lying in a whole bunch of this by degree, but in finitely many spots. So if you look at any one slice of this, then it's natural to expect that proj of R of the ring corresponding to kx plus b plus t1h should be isomorphic to proj of the ring corresponding to kx plus b plus t2h if t1 and t2 correspond to a slope in the same slice. If you have no new generators, there's no reason to expect that the sections in those rings give you different information. This is not a proof. It's just trying to give you some intuition why it should be. So I'm claiming that if this ring is finitely generated, then you expect one minimal model for every different slice, and the slices are just cut out by the different generators. That's just intuition. There's no. I think you can make it into a formal proof, but I'm not claiming that I have done that. Okay. Any questions with respect to?
You said in one word that this right-hand thing can be considered as a low-canonical ring of some one-dimensional platform. So can you explain it?
Oh yeah, I was fearing you'd ask that because I forgot. I think what you need to take is so you take your variety x. You take, let's assume that they're Cartier, otherwise you have to take some multiple. You assume that kx plus b and kx plus b plus h are Cartier. You then can take the P1 bundle corresponding to projectivizing those two line bundles. Of course, this will have trivial canonical ring because it's a P1 bundle. So now let's add two sections. And and maybe you want to add three sections and keep it KLT, and then when you do the push forward, you should get symmetric powers of that vector bundle, right? And what do the symmetric powers of that vector bundle correspond to? I think it works, but I'm not 100% sure that I said all the exact words in the exact order. And anyhow, this is intuition. I will do a formal proof later. Okay, so now we have a little over 20 minutes left, and so now I have to decide what material to present in the rest of the lecture. I have sort of skipped ahead in the notes because one of the things that I did want to do was to actually prove give you an idea. So this is great as intuition for everything, but it would be nice to actually prove some stuff. And one of the things I did want to do is give you an idea of where the cone theorem is coming from, because it's such an important theorem. So what I would like to do is, and I will not be able to do it completely today, but what I would like to do is to prove the base point free theorem. So the first thing I should do is find the statement of the base point free theorem. And I have found that, so at least I can state the base point free theorem. So what I'm going to do is, I think I'll state the base point free theorem. I'll show you why it's relevant to the cone theorem. And I'll start sort of setting up the machinery for the proof of it, and then we'll do the proof next time. So again, apologizing to some of the senior people like Kenji who have probably saw the base point free theorem being born or shortly thereafter. But it is really a beautiful theorem. So, this is not the base point free theorem. It's Kawamata Vivek vanishing. Okay, so let me see if I can find it, and otherwise I will.
Can I ask one more question?
You can.
Before you go on. Is this the behind the scene motivation for you to come up with a MMP with scaling?
This is the motivation, so that we have. That's the only way that we could figure out how to get termination of the minimal model. Right. And this was the intuition on why it should terminate before we proved it. Eventually, you'll see the proof is very formal and different from this, but this was original motivation. And I had an argument to do it this way, but then in the end, James's argument was better. I had to concede. Okay, so this is driving me nuts that I cannot find a statement of I highlighted everything before. Okay, give me one more second and found it. Okay.
Sorry,
Yes.
So you only use this B being big to choose the extreme array.
Well, okay, so I've only used the B being big to make sure that there were only finitely many extreme arrays to worry about. But then when I want to prove something like this finiteness of minimal models, I really need some bigness in the picture.
But you are telling us the finite generation holds without any condition. No?
The finite generation holds without any condition. For technical reason, the finite generation of this mixed object, you need a little bit more. Essentially, you need to know that kx plus b has a good minimal model itself.
Oh, I see.
And yeah.
So,
There are some technical issues that I have not discussed yet. But roughly speaking, everything goes back to the base point free theorem and the non-vanishing theorem. So we'll see in a second why we want to, well, not in a second, it will be pushed to the next lecture, but it's built into the proof of those theorems why you need something big in the picture to get things to work. So let me state the two theorems. So
sorry, I am a pain.
Okay.
I apologize.
No problem.
I'm still a little bit confused. You said finite generation holds for any, without any condition.
That is correct.
And then you explained to me that this mixed low canonical thing is actually low canonical thing of one dimensional higher.
Yeah, but the argument I gave you was a 20-second argument waving my hands.
Oh,
So if you make it precise,
you need somewhere to use the B being.
yeah. Okay, since Kenji is asking this question, let me make another observation.
Sorry about that.
Well, but since you've raised the question, this is, at some point I'm going to have to say this, so let me say it now. So, in fact, finite generation of the ring corresponding to kx plus b is implied from the case when kx plus b is big. So really, we prove this theorem in the case when kx plus b is big, and then we use the work of Fujina Mori to deduce it in general. How does that go? So you look at x, and you consider a map down to, let's call it z, the Ithaca vibration. right? So I'm interested, I'm telling you I want to reduce it to the case when kx plus b is big. So I'm interested in the case where the eta vibration has positive dimensional fibers. So let's just think of the eta vibration birationally. So let's resolve the singularities of this map. So let's assume that it's a morphism. What does the eta vibration look like? It's characterized by the following property. The dimension of z should be equal to the codaric dimension of kx plus b. If you want to think of b equals to 0, there's no harm in that, if you find it annoying. And the property that the codaric dimension of kx plus b restricted to the fiber is equal to 0. Right? That's what characterizes the eta vibration. Okay, so now, by a result of Fujina-Mori, which is somewhat technical, so you have to state it exactly right, but the point is that you can assume the ring of kx plus b some truncation. So let's do it this way. There exists a positive integer k such that the ring corresponding to kx plus b is isomorphic to the ring corresponding to kz plus bz plus mz, where this is a KLT pair, and this gadget here is an F divisor. So this is only true birationally. You have to replace x and z by appropriate birational models. But in terms of the rings, we can assume that the ring corresponding to kx plus b is computed by a corresponding ring downstairs on z. The price you pay is that it's no longer a KLT pair, it's what we call a generalized KLT pair. It's a sort of a KLT pair plus an F divisor. So your first reaction is, I'm screwed because now I'm in a different category. Now I have to prove an even more complicated theorem. But now the fact that, note that kz plus bz plus mz is big. Just by assumption, because this is the eta vibration. So this is going to be Q linear equivalent to an ample divisor plus an effective divisor. Okay, so now things are looking up, because then if I take 1 plus epsilon kz plus bz plus mz, this will be Q linear equivalent to kz plus bz times 1 plus epsilon plus 1 plus, no, I don't want that, kz plus bz, well, plus mz plus epsilon a plus e. Yeah, that's what I want, right? So this is the same as kz plus bz plus epsilon effective divisor plus mz plus epsilon a. Now, look at this. The condition of being KLT is defined by some strict inequality, so it's an open condition. So if I add epsilon times an effective divisor, this is still KLT. This is an F divisor, this is an ample divisor. The sum of an F divisor and an ample divisor is ample, so this is Q linear equivalent to a divisor, let's call it HZ, which is a general ample divisor, so it intersects everything in sight transversely, so the whole thing is a KLT pair. Okay, so this, so let's call this whole thing, let's call this KZ plus delta Z, which is some KLT pair. So then, this will be isomorphic. So let's assume we can replace k by a more divisible integer. So let's assume that k is the form 1 plus epsilon times j. So this will be isomorphic to the ring corresponding to multiples of kz plus delta z. Where now this is a big unkLt pair. And this is finitely generated. So there's one thing that I've really been waving my hands about is the following lemma, which will be necessary later on. And it's a straightforward lemma. A ring corresponding to a certain divisor D is finitely generated if and only if any of its truncation, sort of its Veronese subring, is finitely generated, where this gadget here, what does this mean? This is going to be the direct sum of H0 m k d, where for any m greater or equal to 0. So often we call this, or people call this, the kth truncation. So the claim is that this ring is a finitely generated over algebra with the complex numbers if and only if the corresponding truncation is. And okay, so what's the argument for this? So going one way, going this way, there's a natural group action given by multiplying by a kth root of unity. So if you let zeta to the k equals 1 be a primitive kth root of unity, then you get an action of z mod k z acts on this ring R of D, and the k is just the ring of invariance. I don't know if this is the right way to write it. The invariance of this ring with respect to that action, right? And so it's a theorem of Noether that this is going to be finitely, if you start with a finitely generated ring and you have a finite abelian group, the ring of invariance is finitely generated. To go the other way, let's assume that this ring is finitely generated. Why do you expect that ring to be finitely generated? Well, because this ring is integral over that ring. So D is integral over dk. The reason it's so stupid, but let me just write it. Suppose that you start with f and Rd, then it satisfies the monic polynomial x to the k equals to, or minus f to the k equals 0, which is a polynomial in a monic polynomial with coefficients in this invariant ring. Right, so it's integral over that ring. So another theorem of Noether does it. Yes?
My original question was you wrote kx plus b plus th minimum model is finite when b is big.
Right.
And you explained to us the reason why you should expect it comes from finite generation.
Right.
Of this multi-canonical ring or whatever, box ring.
Well, this fat canonical ring, yeah?
Yeah, but then you told us this box ring can be considered as the KLT canonical ring of some thing. And that, so you are explaining to us the finite generation of canonical ring holds without any.
Right, but obviously I cheated slightly.
Oh, you're cheating.
Yeah. So for that statement to be precise, you need some technical condition, which can be satisfied if B is big. But otherwise, you run into trouble.
So there is some technicality.
Yes.
You haven't told us yet.
Yes, and I'm not going to do it that way, so I won't end up having it.
Sorry.
But yeah, but there are, yes. I didn't mean to make you believe that it was trivial. I meant to make you believe that it's believable. That was my goal there. Okay, so this was an argument to say that finite generation questions for Kawamata log terminal pairs, this doesn't work for log canonical pairs, but for Kawamata log terminal pairs, you can often reduce it to the case where you have a big Kawamata log terminal pair by looking at the eta configuration. There's another reduction that is often used in the field. So remember, I told you you have minimum models if either kx plus b is big or if b is big. Well, there is an easy argument to go from here to here. And essentially, I already did it. So I'd like to emphasize that. Notice that if kx plus b is big, then you can write it as Q-linear equivalent to ample plus effective. So 1 plus epsilon kx plus b, again, is kx plus b plus epsilon effective plus ample. So you can think of this as being another delta where this pair is KLT. And now the boundary is big. And the canonical rings are not exactly the same of kx plus b and of this, but they have isomorphic truncations, right? Multiples of k times 1 plus epsilon of this are the same as multiples by k of this. And also notice that kx plus b dot c is equal to 1 over 1 plus epsilon kx plus delta dot any curve c. So this number is 0, positive or negative, if and only if this number is 0, positive or negative. So running a minimum model program for kx plus b is the same as running a minimum model program for kx plus delta. So often, to prove statements about a big pair, we end up proving statements where the boundary is also big. This is just a technical point. So those two things that I claimed were different are actually the same. And so the focus should really be on the boundary being big. And notice also that when you run your minimum model program with scaling, as long as the scaling factor is positive, you have this extra th, which is big, so the boundary is sort of automatically big. So that's yet another thing that works in your favor when you're running the minimum model program with scaling. That's all waving my hand, so nothing precise. Well, that statement was precise, but...
Wait. So what you said was argue the case with b being big is more general than kx plus b.
That's exactly what I said. The case where b is big is more general than the case when kx plus b is big because I have a reduction from this case to that case that I explained. Okay, so let me at least state the non-vanishing and the base point free theorem, and I just want to make a remark of how it's related to the previous result. So the non-vanishing is really the first step in proving the base point free theorem. So I'm going to consider xb some projective sub-KLT pair. So I'm allowing b to have negative coefficients in this statement. And d is going to be an F Cartier divisor with a property that some multiple, so a times d minus kx plus b, is nef and big for some a greater than 0, and hence all sufficiently big a, right? Because once this is nef for 1a, since d itself is nef, it's nef for any bigger value of a. Okay, then I get sections of OX MD minus the round down of B is non-zero. Okay, so this is sub-KLT. What is that telling you? Sub-KLT means that the coefficients of B are less or equal to, strictly less, not equal to plus 1. So it tells you that the round down of B is, so this is where I round all the coefficients down to the next integer. This means that if a number is less than 1, its round down has to be less or equal to 0. So, so this b is anti-effective. So this minus b is some effective divisor here in this picture. Just to have fix an idea. So if xb is KLT, then this is just saying that h0 of md is non-zero. Right? So, and typical case is d is equal to kx plus b. Well, kx plus b typically won't be Cartier. So d is some multiple of kx plus b. And kx plus b is nef and big. Right? Then a multiple of this minus kx plus b will still be a multiple of kx plus b. So that will still be nef and big. And so we'll get sections. So implies then that the ring corresponding to kx plus b is different from the trivial constant ring in dimension 0.
Do you actually use this sub-KLT statement?
It's just a more convenient statement because we really care about the KLT case, but in proving it, we go to a log resolution and the KLT pair becomes sub-KLT, but this becomes an exceptional divisor, so proving non-vanishing of this is plus effective and exceptional divisor, is precisely the statement we need. Let me now state the base point free theorem.
So you're trying to find a cleaner statement in view of C.
Yes, a statement. I'm already setting myself up to win. So the base point free theorem, and luckily I have to state it in a more precise way. So let's say that xb is KLT. This works in the relative setting, but for simplicity, let me assume that x is projective. D is my nef Cartier divisor. And I'm assuming that AD minus KX plus B is nef and big for some A greater than 0. Then BD, the linear series, is base point free for every B sufficiently big. Okay, so why is this connected to the cone theorem? Well, think of this negative extreme array that you consider. So here's the picture. Here's that negative extreme array that was being cut out by a divisor L, which is typically the form kx plus b plus th. Okay, so let's say that we're in the case where this gadget is big and it's nef by construction in your minimal model program with scaling. Then you're precisely in the case where you can apply the base point free theorem. So you have a nef divisor where some multiple is free. So that means that that nef divisor is actually semi-ample. It defines a morphism for you, and that morphism is precisely the contraction of that ray. So if I prove the base point free theorem for you, I am proving for you the existence of this contraction. I'm also proving this theorem here for you because you see what I'm telling you here is that BD is free for every sufficiently big B. But then you see you think of D as being B plus 1 D minus BD. It's obvious, but now both of these are free and define the same morphism. So both of these are pullback of Cartier divisors on that map. So we have this map from X to W, this map is defined either by this linear series or by that linear series. So this guy here is C upper star of a line bundle LB. This guy here is C upper star of a line bundle LB, and the difference between two line bundles, two Cartier divisors, is again a Cartier divisor. So once you prove the base point free theorem, 3 and 4 are essentially immediate. 1 and 2 are very fiddly. They take work. There's a good proof in Kolar-Mori, but even there I think it's 5 pages, 6 pages. It goes through a rationality lemma, you have to take a whole afternoon and you have to focus very hard to convince yourself that the things are working out the right way. Even though those two are great expositors, it still going to make your head hurt a bit. So I'm not claiming that 1 and 2 are easy consequences. They follow sort of formally, but it's tough. If you think about it, 3 and 4 should seem straightforward consequences. So next time I'm going to start, I'll remind you Kawamata Vivek vanishing. I'll use that to prove the non-vanishing, give you a quick idea of the base point free, and then we'll move on to other stuff in the minimal model. Okay, so let me stop here. Thank you very much.